this computer. Okay, so this one, basically you use the formula is that n is 20. So 20 multiply the average of the head and tail turn. So head is 10. And the tail basically is this one, is 10 plus 19 multiply 3 and equal 10 plus 57 and equal to 67. And so this is 10 plus 67. And so this one is going to be just 10. And this one is 77, so 770 cents. So $7.70. That's the answer. And so it's all very naturally. So if you have any problem, just go for the head, go for the tail, average, then multiply the total count. I think we'll leave most of as the practice, and let's keep going on the geometric series. And geometric series is just a different beast. We're using a different technique. And this technique called scale and difference. So basically, so let's do a comparison for the arithmetic. For the arithmetic, we use reverse and sum. And then for the geometric, we use scale and difference. So this is how this can be done. So again, we assign the variable capital S as the total of the finite sum of the geometric series. In a geometric series, each term, each addend has the relationship of scaling up by R. R is the common ratio. So the second term is R times A. And the third term is basically AR squared, is like R multiplied the second term. So it goes this way all the way. And it's very hard to do the sum if you just do it brute force, but if we scale it, so this basically is the first expression. The second expression is actually just equal to the first expression multiply R. We multiply R on both sides, then SR equals to, then we also, when we multiply it, we also shift the position of the term, each term. So AR, we put it right underneath of, the first expressions, the second term. Then when we do difference is we just minus them. We do a minus. Then basically you will see that the left side became S minus SR. The right side, we basically, these cancel all the way. And only one left is the head turn plus the, actually minus, head turn minus the tail turn multiply R. The tail turn is R to the n minus 1. And tail turn multiply R is A to the R. So basically, this became the equation for the difference of scale and difference. And then we can solve for S. Basically, we factor out 1 minus R. And then S will be equal to A minus A to the R to the nth and 1 minus R. So this formula is actually very easy to remember if you understand the mechanism of this calculation, a scale and difference. So scale and difference, that's why you get 1 minus R, because the sum was scaled. So the minus you have to remember because it's called difference. And scale, you also remember it because it's multiply R, 1 minus R on the denominator. Then a numerator. Numerator is just all about what's left of this whole operation. The whole operation, the first term will survive because after you scale, the first term will shift to the second term. So it only will cancel the second term. So the head will survive. The tail will survive, but not tail itself. The scaled tail, scaled up tail. So because when you scale, the first term shift to the second term, the tail term shift to the beyond the first series tail turn. So it won't be touched. So that's minus A R to the nth. So basically this for me is very easy to remember. I usually actually remember it by like A and 1 minus R to the nth. I actually usually do it this way and 1 minus R. Either way is fine. So basically, you can remember it both way. And this is just, so let's do a few problems and trying to see, how we are going to do it. Yeah. Let's trying to do this problem. Let's find the sum of this 1, 2, 3, 4, 5, 5, 10. 5, 10 obviously is not much. You actually can do it by brute force. But what we are going to do is just by using the geometric theory, because let's see that the first term is 2. The second term is result of 2 multiply negative 1/3. And so basically looks like negative 1/3 is R, is the common ratio. Let's multiply the second term by negative 1/3 to see if we can reach the third term. Negative, negative became positive, and 3 multiply 3 equal to 9. So indeed, it is a geometric theory. So basically, we will say S equal to, so basically is the, remember like scale and depth. Scale and the depth, so you remember 1 minus R. R is where scale happened, and depth is where this minus come from. Scale and depth, 1 minus R. So the top surviving term is the first term, so 2. Also scaled tail turn minus, the tail turn is 281. So, and scale it by this, negative 1/3 is actually this number. So minus R is actually minus negative 1/3. So basically this will be 2, a minus thing is actually plus. So this going to be, if you multiply it up, it's going to be 243 and 2. And 1 minus negative 1/3 equal to 1 plus 1/3. So it's 4/3. And so this equals to 243. And this basically going to be just, 243, and 2 will become 486. And 486 plus 2 is 488. And still divide by 3. And this is 488 and 243 multiply. Divide a fraction equal multiply its reciprocal, so it's 4/3. And this we can cancel, it's 1, 2, 2. And this is actually just 81 because this is 3 to the 5th, 3 to the 1st. So basically, this is actually 1, 2, 2. And so basically it is actually 1, 2, 2 over 81. And let's see whether or not we can simplify logs not. Yeah, co-prime, because this is 3 to the 4th, and there is no factor of 3 on the top. So this is the final answer. And so basically, it usually it tell you the tail turn. So the formula is S equal to A minus A R to the nth divided by 1 minus R. So basically, this is actually just equal to the tail turn multiply R, because the tail turn already told you, so you don't have to calculate from scratch for this turn. That's the trick. Otherwise, you will have to multiply 2, 1, 2, 3, 4. So 2, you have to multiply 2 multiply negative 1/3, and to the 4th, to the 5th actually, because you had to tail turn, you have to multiply 1 more turn. So basically you had to do this calculation. Do this calculation actually, for this case, it's actually as easy because actually I can remember 3 to the 5th and write it out directly, but not a lot of time, it's not that easy, not obvious. Then actually it's advantageous to use the last term. Okay, so let's go to the infinite series. Infinite series is actually a very useful thing, and this is actually calculus, where calculus actually is based. So calculus, a lot of times they can calculate to a concrete number. Why? Because that's actually a converged by infinite sum. Infinite sum is actually just infinite series. And so give you the scope of this. For example, this is a whole thing. And if I draw a second square, and then I split it by half, this is 1/2. Then within the 1/2, I split again, that's 1/4. Then 1/8, 1/16. So no matter how many times you split, it's always within 2 units square. In fact, the total of the whole thing will add up to 2. And so why? So you will ask why? Because this actually converges, and it's just geometric speaking. You can see this will be limited by the big framework of 2 units. And then algebraically, we actually still use the same trick. We're still using the same trick, and but then actually, so this is actually, algebraically you can use 2 ways. So this is just use a limit. For example, the finite The finite sum is this. Yeah, this is just another format of the previous example. So the previous example is it do not factor out A. So if you factor out A, it's just going to be the same thing. So basically, the finite sum of the an infinite series will be expressing this format. But if R, absolute value of R is less than 1, then when n goes to infinity, so if absolute value of R is less than 1, the more time you multiply, the smaller it is. So basically, R to the nth will go to 0. So this term became 0 when n goes to infinity. So basically, the whole sum is actually equal to A over 1 minus R. So that is actually the result. And you actually is also able to use like you can also use like scale and difference. So let me show how to use scale and difference directly to derive this formula. So basically this part is just equal to s. Then we scale on both sides. This is infinite sum. If we scale by r, s going to be ar plus ar squared plus ar cubed plus whatever. And then do you see that the difference between the finite sum and infinite sum is that when you use dealing with infinite sum, and there's no tail turn and so there's no surviving tail turn. When you try to do difference, so r minus, so basically I factor r out, r multiply, s multiply 1, s multiply 1 minus r is actually equal to a, because these terms all cancel all the way to infinity. The only surviving term is a. So basically s will become a over 1 minus r. So with infinite series, it's actually simple compared to this. You have to worry about the tail turn, and in infinite series, you only need to worry about the head turn, then also the method of scale and difference. So basically, this is very easy to do. Okay, so after given this preparation, I think we finally ready to solve the problems that I think Sharon provided. So basically, a solid ball, rubber ball, bounces to 1/4 of the height it is dropped from. What is the total vertical distance traveled by a ball dropped from a height of 24 feet as it bounced to rest? For example, when it hit the floor for the second time, it will have traveled 60 feet. So it's 24 plus 18 plus 18. So imagine this is like 24 feet drop is 24. So you have a one way down in the drop. Then basically you bounce back to 18 here. So here is actually a round trip from the ground. The first bounce, between first bounce and second bounce is a round trip of 18, because 18 equal to 24 multiply 3/4. And so it's going to be bounced lower and lower until its rest. So we're going to calculate the whole thing. And it looks very daunting, very dreary. situation, but it's actually very simple. Just infinite theory. Infinite theory is actually A, sun equal to A divided by 1 minus R. A is the surviving term. It's the only surviving term at the head. Then it's the ratio. And the ratio here is actually, is absolute value of the ratio is equal to 3/4 is actually less than 1. So basically it's a converging geometric theory. And so we listen is at 24 plus 18. 24 is on the way down. Then this is on the way up. So this is down. And this is up. And plus 18 is on the way down. And then plus 18 multiply 3/4. And that's on the way up. Then plus 18 multiply 3 to the 4th. That's on the way down. So basically, we kind of checking the pattern of this. And then we will just sum up two geometric theory. One is on the way down. On the way down, it's just always 3/4 multiply its original term. Then on the way up, this is on the way up. It's also just, to the 3/4. So basically, the total distance is the travel is going to be, let's say D equal to 24 plus 18 is just, I'm going to write 18 the way that, represent the geometric sequence relationship. 24 multiply 2/4 or 3/4. And then plus 24 multiply 3 to the 4th. So this is 2 leg. So this is the way on the way leg down. Then this is on the way leg up. So 24 multiply 3/4 is just 18. So basically, then on the way down, it's going to repeat this again. So basically, it's going to be 24 multiply 3/4 square and the minus also plus 24 multiply 3/4 square. So given this situation, we just calculate two theory. One is that 24 plus 24 multiply 1/3/4 and plus 24 multiply 3/4 square plus all the way to infinity. Then the second is 18 plus 18 and 3/4 and plus 18 and 3/4 square and plus all the way to infinity. Notice that because one leg is down, one leg is up. So this sum is all the distance on the down leg. This is on the up leg. But we can add them up. If we add them up, what we get is actually 42 plus 42 multiply 3/4 and plus 42 3/4 square and plus all the way to infinity. So basically, with this geometric theory, it's because infinity, so that's make it easy. So the A is actually equal to 42. So 42 is the A. So A will be on the top. And then on the bottom will be 1 minus R. One minus 3/4. So equal to, 42 equal to A. Let me just write 42 here. So basically it's 42 and 1/4. So divide by 1/4 equal to multiply 1/4. So 42 multiply 4 equal to 168. So that's the answer. So it traveled 168 feet until it go rest. I think this is Sharon's problem. Sharon, did you understand it?
Yes.
Yeah, so it's just about, you know, two geometric theory and sum it up, you will get it. Okay, so let's go to the next topic. Yeah, this is a, so we also check diverge theory. And diverge theory, obviously, this is a very obvious to tell it's diverge. 1 plus 1, if you adding 1, it's going to be infinity. So if you add it, it's going to be infinity. So it's anything goes to infinity, it's diverging, it's not converging. And this one, you know, the sum of the first term is just 1. The sum of the second term, 2 term, is -1. Then the sum of the first 3 term, so is actually 2. So basically, you know, you will see that it's actually will keep growing. It's going to be going fairly big, and um, so it didn't converge. And also do you see that, you know, it kind of flip flop, because the sign is that sign changes, and for infinite theory, it's actually, there's a fairly fun thing to watch, is that depending on how you stop at the last turn, it could go to, you know, for example, you can group it this way. If you group each 2 turn by pair together, it's the 2 turn going to be -1, -1, so 4 turn. If you take even turn, if you take even turns, it's going to be just -n divided by 2. So for example, if you get 2 turn, it's just going to be -1. You get 4, you get -2. And if you go to infinity, it's actually, you know, a negative. The total of, if you group this way, it's going to be a negative infinity. Then, but you can group the other way. You actually can. So diverge has a lot of a lot of format, and so we basically are dealing with infinity. So when going to the infinity, it's going to be very strange. So if you add it up this way, if you pick even term, or if you got odd term, then the finite sum, if odd terms, the first term is just 1. If you take 3 turn, it's going to be 2. If you get 5 turn, it's going to be 3. So in fact, the finite odd turn sum going to be like 2n. 2, it's actually going to be m plus 1 divided by 2. So basically, so even turn sum, even turn finite sum is negative and divided by 2. because if you have 2 turn, 2 divided by 2, yeah. So basically, so this diverge. So the finite sum just going to be flip flop, and its oscillate became, and the oscillation became bigger and bigger, bigger and bigger, because each turn, each tail turn became so big that change the sign, different swing the whole result. So basically, this is type of the diverge, and so one. So what we see is that for a infinite series to converge, the first condition is that the last turn, the tail turn, need to become smaller and smaller and smaller and smaller. Otherwise, it's not going to converge. Even it's a constant turn, you can add up to infinity. So basically, it's just going to shrink. The only way to shrink is that the R, the common ratio, the absolute value of common R is going to be less than 1. So when you talk about infinite series sums, only one absolute value of I is less than 1, it became useful. So this one, and so a lot of turn, even each little turn actually goes to 0, because this is a sum of the reciprocal of natural number. So if it's a non-natural number sequence is 1, 2, 3, and all the way to infinity, and this is just reciprocal of them, and the total of them actually will not converge. It it's not going to converge. It's going to go to infinity too. How does that happen? Let's check. So for example, if the first term is 1, if we add 2 turn, just pick 2 turn, 1/2 plus 1/3, and um, let's group those 2 terms together, and then begin to group those 2 terms. And let's do it differently. Then let's group this as 1, and then let's group those 3 terms. Those 3 terms will add up to bigger than 1, because you see the middle term, the last term is 1/4. This is bigger than 1/4, and this is 2 1/4 is 1/2. This is bigger than 1/2. This is 1/2 plus a bigger than 1/2. So this is bigger than 1. So I can always find a group of numbers, and next group of number I can add up to at least 1 is from 1/5 add up all the way to 1/16. So basically, because here is we can add up to 1/8, and then we can add up 1/9 too. So let's check those 2 group. So here we have 1/5 plus 1/6 plus 1/7, and each term is bigger than 1/8. There are 4 of them. So 4 multiplied 1/8 equals to 1/2. So basically those 4 terms is bigger than 1/2. And there are 7 terms here. There are 8 terms here from 9 to 16. And these terms, each one of them will be bigger than 1/16, and you have 8 of them. 8 multiplied 1/16 is actually equal to 1/2. So basically, this group from 1/5 all the way to 1/16, the total of them will be always bigger than 1. So basically, you can always so what you can find is the first term is 1, the second term is to the 4 to the 4 to the first. Then 4 between 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 1 between 2 and to the 4 to the first, and between 4 to the first plus 1 all the way to 4 to the second, you also is the total of this reciprocal also bigger than 1. So you can always keep this pattern going, that if you grab enough turns, it's always you can get an extra 1. So when going to the infinity, this will be bigger than um, infinity. It is infinity. And um, then when you began to do with the um, there's a there's a very useful shorthand for the summation, also for the product. So this is sigma, and this is pi, and sigma basically is the Greek letter for S, and pi is the Greek letter for P, and S stand for sun, and P stand for product. So basically, it's a very natural to link those sign with a shortcut for the summation and continuous product. So for example, this one is that K is the dummy variable, which is used as if in a computer programming language as a like a loop variable. So all it says, treat this as an instruction, programming instruction that like, K start from 1 and increment. And in computer, you can choose the like loop step to be not 1. But in the math, the loop step of the summation and the product always will be 1. So basically, you read this by K start from 1 will end at 5, and each step will increment by 1. So basically, if increments this way, you just counting from 1, 2, 3, 4, and 5. You count 5 number. So for those 5 number, the meaning for this sign is that for those 5 number, sum them up. So basically, it became you convert the sequence into series. So this is just a shorthand for the. So if you get yourself confused, always try to read as a programming language instruction and write it out as a summation in flattened form, so you basically is able to better interpret it. And here is that there are several rules you can follow. Is that if there's a common factor, you can always extract it outside of the sigma sign. And if you have 2 terms with in the parentheses of sigma, is actually Q-splitting. So it's just associative. You can, because you can redo the association and tear them up. Yeah, so here are a few examples. So K does not has to start from 1. So this is the first example from 1 to 5. It could start from a higher number. For example, here, when you do this type of sum, you just write it out. Don't try to do something special, just literally expanding it. So 2 is still 2. K, the first K start at 3, so 2 to the third. And sigma means that plus, so we need to plus everything together. So plus 2. So I used 3. The next value I'm going to pick is 4. So I'm going to plus 2 to the fourth, then plus, and then going to go up one more step, 2 to the fifth, then 2 to the sixth, then 2 to the seventh. We end up 2 to the seventh, so that's all we need to calculate, and that's it. And yeah. So I'm going to do one more example. Let's going to go to the next topic. And for example, for this one basically is a arithmetic theory. And the arithmetic theory, so the first term, A1 equal to A equal to 13. And this is the last term. And the common difference is actually negative 1/2. So basically, then we have to count how many terms we have in this theory. And to count the terms, it's actually quite easy. It's actually the last term minus the first term divided by common difference plus 1. So the last term is negative 1/2 minus the first term is 13. And divided by common difference is negative 1/2. So basically this, and also plus 1, because this is the gap, total gap size divided by a single gap size. Then you get a gap count plus 1 is the total count. So here, because everything is negative, we just multiply negative 1 both on numerator and the denominator. We will make them positive. Actually, this actually is positive. So basically, positive minus negative, then if we multiply negative, then it's going to be negative. It's going to be this way. So 13 minus is just 12.5. 12.5 multiply this, going to be, divide this, multiply 2 is going 25. 25 plus 1 equals 26. So it has 26 turns. It has 26 turns. So basically, we actually will have, we can do I from 1 all the way to 26. So that's the way to write the sigma, convert a expanded form into a shorthand form. And then we will just writing the, term formula for the, so A is 13 and plus I minus 1 and multiply the common difference is negative 1/2. So this is going to be our, summation sign for this, shorthand for this. And you actually can do certain, manipulation to simplify it. For example, sigma I equal to 1 to 26. And this is 13 minus 1 half I and minus equals positive, so plus 1 half. So basically it's actually equal to 13 and 1 half minus 1 half I. So you basically can simplify it to this point. And sometimes you can even extract out the 1 half to the outsides. For example, you can do certain conversion, but those are pretty much equivalent, don't add much value. For example, you can extract the 1 half out. If you extract 1 half out, you have to write this as an improper fraction. Improper is 2 and 27. So basically, that's going to be 27 minus I. So basically, that's the way that you can write it. Okay, so that's the summation. And yeah, this is, in addition to summation, there are product. Product is just using, not sigma, just using pi. And this is just, for turn, x minus 1, x minus 2, x minus 3, x minus 4 is k equal to from 1 to 4, x minus k. So this is just one single example here. And so we talk about the series, then there's also sequence. And sequences are just numbers, list of numbers. This is 1, 1, 1, 1. This is a constant sequence. This is a even number. This is the reciprocals by alternating positive and negative sign. So a lot of time, in the test, maybe they will ask you for the closed form. And so basically, you can write the first one. So this is a shorthand for the sequence. It's just, the curly brace followed by the formula which represent this sequence. For example, the first one is just represented by 1, and the second represented by 2, and the third one represented by -1 to the n plus 1's power multiply 1 n's. And in addition to this type of these are the closed form, and it's just written by a formula. Some of the sequence are so complicated that it's very hard to write a closed form by just a single formula. Fibonacci actually is possible to write by a single formula, but if we really want to see how complex is that, we're going to do that if we have time in the future. So the Fibonacci actually not this one. Yeah, Fibonacci is just way more complicated. It's so because it's closed form like this just have a lot of radicals. It's one radical plus another radical and with another radical coefficient. So it's a very hard to remember, very hard to use form. So basically it's using a recursive form. And recursive form is that recursion is that, it starts from F0, F0 equals 0, and F1 equal to 1. Then after defining the first term by fixed number, then we just define the rest by using the rule, how to build the next term. So to build the next term, Fn equal to Fn minus 1 plus Fn minus 2. So that all the meaning is that just we adding the previous two term to get the next term. So 0, 1, adding 0 and 1, we get 1. So this is F2, F2 equal to 1. Then F3 is that 1 plus 1 equals 2. So F3 equals 2. And 1 plus 2 equals 3. So F4 equal to 3. So 2 plus 3 equal to 5. So it's F5. So basically it's just going on and on like this. It's messed up. Let me try to, yeah. So basically, these are the the sequencing shorthand. So for example, let me just one example. So write this sequencing the shorthand. So every turn, including the first turn, need to fit this pattern. And we see that this is n equal to 1, this is n equal to 2. And it's actually increment. It's actually, is -1. So it's the common difference is -1. So basically, -1 and -n has to be in this formula. Then all we need to determine the initial shift. Then we will finish this form. And for n equal to 1, the A1 equal to like a number x minus n equals to 10. And this is 1. So basically x will be 11. So basically, given those information, I know that closed form for this sequence is 11 minus n. And we can double check it. When n equal to 1, that's going to be 10. N equal to 2, that's going to be 9. So this actually works. So this is the sequence. And I also going to do a recursive um, representation for arithmetic. And so for arithmetic, for example, the recursive form is that, actually A1 equal to A. Then AN is actually equal to n minus 1 plus D. So this is the recursive form. And you can try to do for the geometric, it's very simple. Let me finish this part. So this comes to, you know, why. So why arithmetic term, arithmetic theory is called arithmetic theory, and why geometric theory is called geometric theory. It actually has some meaning. So basically, in an arithmetic sequence, every term is the arithmetic average of adjacent term. How does that works? So for example, we know that, you know, xn equals to a plus m minus 1d, and x m minus 1 equal to a plus n minus 2d, and x m plus 1 equal to a plus nd. So basically xn is actually equal to x m minus 1 plus x m plus 1 over 2. So you actually can fill in the numbers and prove it very easily. So this is x m minus 1, just use this plug in here. It's going to be a plus m minus 2d plus a plus nd divided by 2. And so we can tell that they are 2a. So basically, and 2a divided by 2 equals a. And here we can tell that they are 2nd. And so basically 2nd divided by 2 is nd plus nd. And we also have a negative 2d divided by 2 is negative d. So basically equal to a and the plus, we can factor out d, then m minus 1d. M minus 1d is actually exactly equal to this. So basically, you know, in a arithmetic sequence, each term is the average, arithmetic average of adjacent terms. And then in a geometric sequence, basically, each term is the geometric average of adjacent term. For example, you know, an equal to a multiply r to the m minus 1, and the a m minus 1 equal to a to the r m minus 2, and a m plus 1 equal to a multiply r to the n. So basically, you know, this term is actually a geometric average. Geometric average of two terms is just product of those two terms and take square root. So basically, we will see that a minus 1 equal to a multiply r to the n minus 2 multiply, then multiply this one, a multiply r to the nth. Then the product of them, then square root. And this actually, you know, we have a square is just a. And this is r to the nth. So inside it is r to the, this is 2n. n plus n is 2n. So 2n minus 1. And square root just takes this apart. So a r to the n minus 1. So a r to the minus 1 is just equal to this. So basically, you know, the square root. So basically a m minus 1 multiply a m plus 1 square root. This is a, this is not d. And, you know, equal to this, and basically will be equal to a to the r to the n. So basically, you know, this is just the, you know, the origin of its name and its meaning. And there are a bunch of exercise. And so I think, yeah, I think we are able to cover the whole chapter for. It looks like chapter 24 is actually, looks like a higher number, but it's actually in a lower part because we actually have two bulk. The main bulk we are doing is that the main bulk we are doing right now. We switch to those two bulk. The other problem solving volume 1 and volume 2, and both of them has a chapter on the sequence and series. So we are able to finish this part, and we still have a whole chapter that dig deeper into sequence and series on the book 2. And anyway, I don't think we have enough time to cover it. And I will try to compile the exercise list and send it out. And also the middle school computation math also have a very short, mention on the sequence and the series, but it's too concise. It's just too brief and not deep enough to really cover the computation material. So I kind of just switch book and use a different one. And okay, I think that's all for today. And we'll have that nice one. I will send out the practice material after the in the night. Okay. Bye
Thank
bye.
you.
Hi. Yeah. Thank you.